Alright, hi AP Chemistry. This is the valence shell electron pair repulsion video, doing this one on the cuff because I need it like in 24 hours. So watch the video and we'll discuss it at greater length the day after it's assigned. Alright, valence shell electron pair repulsion, VSEPR for short. The structure around a given atom is determined principally by minimizing electron pair repulsions. The structure around a given atom means, in a Lewis structure, the central atom, the electron pairs are trying to minimize repulsion. So they're forming structures based on this VSEPR model. Note the words, note the title. Valence shell, electron pair, repulsions. What you're going to be able to do after this chapter is over, you are going to draw the correct Lewis structure, which you have done first year chemistry. You are going to determine orientation and geometric shape of the structure, also first year chemistry. You're going to determine the bond angle of the structure based on bonded and non-bonded electrons, polar molecule or not. Again, all of this still from first year chemistry. Hybridization is chapter 9, section 1. I'm not going to do a video on hybridization. There'll be a little blurb in this video. Hybridization is really easy for us. We don't get real deep into it. If you can count, you can do hybridization. So that's going to be real simple. Number of sigma and pi bonds, which is a definition. So, alright, orientation around the central atom is the total number of pairs of electrons around the central atom. And the orientation can be different from the geometric shape. Please remember, orientation is the total number. It's the bonded pairs and the non-bonded pairs added up. So count the pairs of electrons. Double or triple bonds are counted as one orientation. Steric number, orientation, arrangement, domain, same thing. How many pairs of electrons are around the central atom? Note the term. It's not asking you how many electrons are around the central atom. It's asking you about the number of pairs of electrons around the central atom. Geometric shape might be different than orientation. The geometric shape is the actual shape of the molecule. So if the question says, what shape is this molecule, think geometric, not orientation. The geometric shape of the molecule might be different from the orientation. The geometric shape is based on the number of bonded pairs versus non-bonded pairs of electrons. Non-bonded electrons need more room than bonded. Lone pairs need more room, so they actually squeeze the remaining bonds closer to each other, so the bond angles between the remaining bonds with lone pairs around the central atom gets smaller. And most of the orientations just say less than when you have lone pairs, with the exception of tetrahedral. Geometric shape will depend on how many pairs of bonded electrons there are around the central atom. So again, orientation is bonded and non-bonded. Geometric shape is bonded versus non-bonded. You have a packet in your possession. It's the same packet you had first year chemistry. There are 5 basic categories of orientations, aka domains. All 5 have no non-bonded or lone pairs of electrons around the central atom. That means the orientation will be exactly the same as the geometry. All right, I'm going to say that again. No lone pairs or non-bonded electrons around the central atom means that the orientation will be exactly the same as the geometry. There are 5 basic categories: linear, trigonal planar, tetrahedral, trigonal bipyramidal, which I call trig-bippy, and octahedral. For orientation number 2 through 5, which is trig-planar, tetrahedral, trig-bippy, and octahedral, There are different geometric shapes based on the number of bonded pair of electrons versus non-bonded pairs of electrons. For the linear, all the other 2 through 5, they have subcategories of linear. That very first linear that's listed is usually a binary. Any basic geometric shape with same terminal atoms and no non-bonded or lone pairs of electrons will be a non-polar molecule regardless of if always count double or triple bonds as one, whether we are doing orientation, domain, and when we get to hybridization they are counted as one. Hybridization, and we'll discuss hybridization again in class. There's no separate video for hybridization. Hybridization is a model to explain bond lengths. It's a mixture of orbitals to accommodate electron pairs around central atoms. They are mutant orbitals made from the sp-df original orbitals. Possible hybrid orbitals will be sp, sp2, sp3, sp3d1, etc. And these are very familiar. They should look very familiar to you. We're going to keep hybridization really simple. We're only doing section 1 of chapter 9. We're going to keep it nice and simple. If we can count, we can do hybridization. That's how simple it's going to be. To determine hybridization, and like I said, we'll discuss this in class at much greater length. You're going to count the total number of pairs of electrons around the central atom. This is the same number as orientation. Total pairs around the central atom. Includes bonded and non-bonded pairs of electrons. And again, double and triple bonds count as one hybridization. Alright, definitions, sigma and pi bonds. Sigma bond, with the little symbol there, the pair of bonded localized electrons. This is that original first localized electron, that very first line you put to attach a terminal atom to a central atom. That is a sigma bond. A pi bond, with the symbol pi, that's the pair of bonded delocalized electrons. That's any extra line you place between the terminal and the central atom. If it's a triple bond, the triple bond will consist of a single sigma, one sigma bond, and 2 pi. The sigma bond is the localized pair of electrons between the terminal and central atom. This is the original first line you draw. The other 2 lines were drawn because you came up short on the central atom, and you had to accommodate that shortness or that lack of electrons around the central atom with a triple bond. These 2 lines here of the triple bond are considered 2 pi. They are the delocalized electrons that move around. The total number of bonds, sigma plus pi, will be equal to the total number of lines in your structure. Alright, Ch4, methane gas, carbon tetrahydride. Total number of valence electrons, 8. Alright, so here is the methane molecule. 8 electrons, 8 valence electrons. Carbon is the central atom. I've depicted it slightly different than normal. The wedge indicates coming out of the plane of the paper, and the dashed line indicates going back from the plane of the paper. So I kind of drew it 3D. There are 4 domains / orientations around the central carbon atom, which indicates a tetrahedral molecule. There are absolutely no lone pairs or unbonded pairs on the central atom. Therefore, the geometry is also tetrahedral. Bond angle 109 degrees. The molecule itself is not polar because the carbon to hydrogen bonds are not polar. I gave you that exception to the rule last Friday. Also, even if the carbon-hydrogen bond was polar, because of the position of the bonds, because bonds have magnitude and direction, since there are no lone pairs, each of those bonds would be opposite but equal and cancel out. Hybridization, it's a counting issue. You count each orientation. 4 bonds, S, P1, P2, P3. Why isn't it S2? Well, because S can't be a 2. S is only one box, one orbital. P's only has 3 orbitals. So once you get the P's all used up, you go to the D's. Well, this doesn't have another bond. So there's only 4 bonds. There's only 4 hybrid orbitals. sp3, that means they took an S and 3 P's and poured it in a mixture, and it came out as a hybrid or mutant orbital that these guys sit in. Ammonia gas. Alright, ammonia Nh3, also known as nitrogen trihydride. 8 valence electrons in the structure. Nitrogen is the central atom. There are 3 hydrogens branching off the nitrogen, and again I kind of tried to draw it in 3D. The wedge is coming out at me. The dashed line is going behind the plane. It used to be the plane of the paper, now it's the plane of the computer. And the solid line is in the plane of the paper with a lone pair on nitrogen, which is very typical for nitrogen. The orientation is 4, tetrahedral. There are 4 domains or orientations. There are 4 pairs of electrons around the central nitrogen atom. That is tetrahedral orientation. The geometry is different because of the 4 pairs, 3 of them are bonded, 1 of them is not. That means it's a trigonal pyramidal geometric shape. Bond angles, because the lone pair requires much more room than the bonded, and I'm going to draw it. What happens is that electron cloud of the lone pair squeezes these guys down closer to each other at 107 degrees. The original was 109, but the lone pair squeezes them down to 107. Lone pairs need more room than bonded pairs. Polar molecule, absolutely. Polar molecule, absolutely. The nitrogen is more electronegative than the hydrogen. So the shared pair of electrons is closer to the nitrogen than the hydrogen. The nitrogen is becoming slightly more negative, and all the hydrogens are becoming slightly more positive. Because there's no bond up here to cancel anything out from down here, it will be a polar molecule because of that lone pair. Hybridization, again, a counting issue. You count the domains, the pairs of. There are 4 domains, S, P1, P2, P3. Even a lone pair has to have a hybrid orbital. Also a definition. This lone pair right here on nitrogen can form a coordinate covalent bond. Something like boron trifluoride could come along and latch onto it and form a coordinate covalent bond. A coordinate covalent bond is when that bonded pair of electrons is supplied by the one atom. And in this kind of example, it would be supplied by just the nitrogen. The boron has no claim to either one of these electrons. They are strictly from the nitrogen. So that's a definition, coordinate covalent bond. And last example, and we'll do plenty in class. All right, this is another example. This is water. Again, orientation is tetrahedral. Orientation is the number of bonded and non-bonded pairs of electrons around the central atom. 1, 2, 3, 4. There are 4 pairs of electrons around the central atom. Geometric shape is bonded versus non-bonded. There are 2 bonded and 2 lone pairs or non-bonded. The bond angle then, because the lone pairs need so much more room than the bonded pairs, the angle between the bond gets smooshed to 105 degrees. Tetrahedral's the only one that will give you specific bond angles for lone pairs. 109 is the original, 107 with 1 lone pair, 105 with 2 lone pairs. Everything else just usually says less than. Polar molecule, absolutely. Oxygen is way more polar than the hydrogen, so the electrons are being drawn to the oxygen. So the oxygen end of a water molecule is always way negative, and the hydrogen ends are always very positive. Water is a very polar molecule. There's nothing to cancel out these 2 vectors, these 2 bond vectors, so of course it's a very polar molecule. Hybridization, again, is a counting issue. Hybridization gets a lot more involved than just counting, but we're just going to count. S, P1, P2, P3, so it's an sp3 hybridization, and again, even lone pairs require a hybrid or mutant orbital, and there are 2 sigma bonds. Any other examples we are going to cover in class?